Hi guys, my name is Kirubanawasu and my metric number is 194,896. So today I'm going to talk about how does the refrigerator works by transferring heat under heat transfer concept. So before I go into furthermore explanation, I would like to do some small demonstration. Actually, this is hot water which I just boiled, and I'm going to place it in the refrigerator for now. And after the explanation we are going to come back to this demonstration. So let's watch some graphic visualization together. There are 5 major components in a refrigerator: the expansion device, compressor, evaporator and condenser coils, and the refrigerants. The refrigerant is a liquid that enters in the expansion device. As the refrigerant passes through, the sudden drop in pressure expands and cools the refrigerants and turns it into gas. As the gaseous refrigerant moves through the evaporator coil, it absorbs and removes heat from the foods. The compressor forces the refrigerants, raising its temperature and pressure. This hot and high pressure gas flows through the condenser coil at the back of the fridge and radiating the heat to the atmosphere, and the refrigerant cools back down to the liquid and enter the expansion device.
Five minutes later.
So it's about 5 minutes, so we are going to check out the result. Oops, it's still hot.
20 minutes later.
So now it's around 25 minutes. We have readjusted the timing, and the water is actually quite cold, and I don't have a thermometer, so I couldn't check the temperature of it yet. So as we watched the animation just now, it actually works by the explanation they given. The hot water, the heat from the hot water actually been absorbed by the refrigerant, and which will be released through radiation process by the condenser coils. So that's how the temperature of the water goes down from hot to cold.
So, just now, my friend Kiru explained about the heat transfer concepts and processes that are involved in a refrigerator. So, I will now continue with the calculation part. So, let's look at the sample calculation. So, it is wished to freeze 15 tons of fish per day from an initial temperature of 10 degrees Celsius to a final temperature of -8 degrees Celsius using a stream of cold air. Estimate the maximum capacity of the refrigeration plant required if it is assumed that the maximum rate of heat extraction from the product is twice the average rate. If the heat transfer coefficient from the air to the evaporator coils, which form the heat exchanger between the air and the boiling refrigerant, is 22, calculate the surface area of evaporator coil required if the logarithmic mean temperature drop across the coil is 12 degrees Celsius. So basically, this example is about the freezing of the fish in a refrigerator. So we can note that the question is asking us to find the surface area of the evaporator coil. So let's move on to the solving the question. The formula for enthalpy change in fish is equals to heat loss above freezing plus heat loss below freezing plus the latent heat. So let's look at the method to solve the question. From the tabular data, the specific heat of fish is 3.18 above freezing and 1.67 below freezing, and the latent heat is 276. Enthalpy change in fish is equal to heat loss above freezing plus heat loss below freezing plus latent heat, which is equals to 321.2. Total heat removed in freezing is equals to 15 times 1000 times 321.2, which is equals to 4.82 times 10 to the power 6. Average rate of heat removal is equals to 55.8. If maximum is twice average, then maximum is equals to 111.6. The coil rate of heat transfer is equals to UA times heat delta T, and A is equals to Q over U times delta T. So the answer is equals to 420 meters square. So the great advantage of tracing the cycle on the pressure or enthalpy diagram is that from the numerical coordinate at the various cycle points, performance parameters can be read off or calculated readily. So now I will explain about the application of heat transfer in industry. The thing that I'm going to touch today is feed water heaters. So feed water heaters are heat exchangers. They're designed to preheat boiler feed water by means of condensing the steam extracted from a steam turbine. So I will show a brief picture of the components of the feed water heater. So as we can see, the steam of turbines goes into the condenser. So the water from condensed steam enters the feed water heater rail. So the heated water from feed water heater train now moves to the boiler, then turbines. Then the process is again going on. So the tube side fluid remains enclosed in the tubes and does not mix with the shared side fluid. Heat transfer within the vessel occurs by means of both convection and conduction rather than combustion alone. Unlike the surface condenser, the flow rate of steam into a feed water heater is not limited by the amount of available steam. Cell shared operating pressure in a feed water heater is determined by the pressure of the steam rather than by the amount of heat transfer surface.
So here's the shell and tube heat exchanger of the feed water. So here we can see the shell with two tube passes with one shell, and here the flow of water, cold water, which is in this journey to the boiler. Here and here's the condensed water from the steam, from the hot steam. So here we can see the cold water will flow through the small tubes inside, but will have contact with one of contact is actually the convection process with the hot fluid coming from here from the turbine from the steam. So the tube is surrounded by the steam, the hot fluid. So eventually the temperature from the hot fluid, the heat from the hot fluid will transfer to the cold fluid coming, which is in the journey to the boiler. So eventually the cold fluid will get hotter and will move towards the boiler, and the the steam which is condensed into hot fluid, which gives energy to the heat to the cold fluid, will eventually loses all its heat, and it will become normal cool water and will move out of the shell. So this is the visualization, this is the process happening inside the shell and tube heat exchanger. Now we see the methodology for heat exchanger design calculation. There are two methods, which are the log mean temperature difference and the effectiveness NTU method. So uh, first, both these methods can be used to calculate the design and also the performance. As the log mean temperature difference got some limitations, we focus on the effectiveness NTU method. So there are several formulas that we need to take into consideration. The main one is this one. This is one over UA, which is the overall heat transfer coefficient, which is equal to 1 over HA. H is the coefficient of convection, and another 1 over HA, which is this one for cold fluid, this one for hot fluid, and built-in the conduction resistance, if there's any. Then after that, got efficiency formula, which is Q over Qmax. Q is the actual heat rate over maximum heat rate in a heat exchanger. So the maximum heat rate can be calculated using this formula, where the C is the capacitance, heat capacitance of the fluid. The minimum refers to it can be a hot or fluid, depends which is the lower heat capacitance, and the temperature difference is T hot initial minus T cold initial, which is because this is the maximum temperature difference available in the heat exchanger. And there is a formula to calculate NTU using UA over C minimum. Then there is efficiency, another formula for efficiency, where it is a function of NTU and CR. CR is the capacitance ratio. If both the fluids in the shell and the tube is the same, then we can assume the capacitance ratio is 0. Then we add another formula, which is the efficiency equal to 1 minus exponential negative NTU. We see how we're gonna use this method briefly in a case study after this. Okay, now we see the case study. A feed water heater that supplies a boiler consists of a shell and tube heat exchanger with one shell pass and two tube passes. 100 thin wall tubes each have a diameter of 20 mm and a length of 2 meter. Under normal operating conditions, water enters the tubes at 10 kg per second and 290 Kelvin, which is the temperature, and is heated by condensing saturated steam at 1 atm on the outer surface of the tube, which is the shell. The convection coefficient of the saturated steam is 10,000 watt per meter square Kelvin. So we're going to determine the water outlet temperature. Here's the schematic diagram of the following the previous problem, and here are the properties of the fluid. Here both the fluid is the same. So even the shell and the tube, both the fluid is the same. The same property. First we have one coefficient of convection, so we need to find another coefficient of convection. So we first calculate the Reynolds number of the tube, then we calculate the Nusselt number. From there we found the coefficient of convection of the tube, and from there we found the overall heat transfer coefficient using both the H, and we found the area equal to the 100 tubes multiply the circumference times the length. Length is 2 meter, and both the lengths, so 2 times 2 meter, and see the capacitance. Capacitance calculated by multiplying the volume rate with the mass rate with the specific heat capacity, and from there, from the values, we calculate the NTU, and we have the NTU, so of course we can find the efficiency using this formula, as both the capacitance same for both fluid, and then we can find the maximum heat rate using this formula, as we have all the values, and we have the maximum heat rate of the heat exchanger and the efficiency, so we can find the actual heat rate, and we found the actual heat rate, and from the actual heat rate, of course, we found the temperature difference, and we have the equation, so we rearrange it to find the output temperature of the water. which is on the way to the boiler. So from there we found the temperature. So that's all for this group project, and thank you.